All right, everyone, I think we're going to get going. So, good afternoon. Thank you all for coming. This is very exciting for us. I'd like to give a warm welcome to our students, our faculty, staff, alumni, and of course, all of our distinguished guests. My name is Jacob Bortnick, and I have the pleasure of serving as the faculty director of the UCLA Space Institute and the department chair of the Department of Atmospheric and Oceanic Sciences here at UCLA. I also want to take this opportunity to introduce our newly appointed executive director, Dr. Ranga Ramachari. And by the way, all the exhibits out front are thanks to Ranga. Ranga, do you want to say a couple of words?
Sure. It's a pleasure to have all of you here. Chemistry is a fundamental part of space because all of you were once inside a star. Remember that? The universe was only hydrogen and helium in the beginning. Everything else was cooked up inside a star. And so every constituent of you was once inside a star at some point in the past. And today's presentation, I hope we put on a good show for you so you understand the importance of material science and chemistry when it comes to space. But what happens in this auditorium is not the end of it. Please come afterwards to the reception where we have actual space materials for you to touch and play around with. So these are both things that will go into space in the future and things which space delivered to us. So welcome.
Thank you. Thank you so much, Ranga. So a few words about the Space Institute. SPACE is actually an acronym, S-P-A-C-E. It stands for Space, Planetary Sciences, Applications, Communications, and Engineering. It is a transdisciplinary and interdepartmental, meaning that it's a campus-wide UCLA community of faculty, researchers, engineers, and students that are all seeking to elevate space science through fundamental space and planetary physics research, technological innovations, and holistic education. And we don't just stop at training PhDs, but we have outreach and undergrads, a professional master's degree that is soon to be formed. And of course, engagement with the public sector and space industry. For decades, and I mean since the 1940s, UCLA has been a leader in this field. And space is having its moment now. I think many of you have probably seen some of the auroras we've had in the past week or two. Some of us have seen the amazing SpaceX kind of catching its Starship back, an incredible technological feat. So space is having its moment, and we're excited to not only be taking part in this new space renaissance, but in some ways also influencing Space 2.0, which is largely taking part here in Southern California, kind of in our backyard. Bruins have made numerous discoveries over the years. For example, finding evidence of a liquid ocean below the icy crust of Jupiter's moon Europa. And of course, we've all seen the launch of Europa Clipper, I think, this past week, and that actually had a UCLA magnetometer on board from right here. So that was kind of fun. Reporting the farthest active comet and most distant star ever observed, discovering supermassive black hole at the center of our galaxy, operating the ground-penetrating radar on NASA Mars 2020 Perseverance rover mission, pioneering the use of CubeSats for discovery science. We can actually make some actual real discoveries with tiny little CubeSats. Solar sails for rapid propulsion that go over 200,000 miles per hour. This is a reality now. And using advanced techniques in artificial intelligence to predict space weather in the Earth's near space environment. And on and on. Bruins have leading and are still leading the space science and technology in so many areas. Today, the UCLA Department of Chemistry and Biochemistry and the Space Institute are delighted to present our joint workshop entitled Chemistry and Materials for Space Science and Technology. This workshop aims to expose both the space science community and the chemistry community to potential areas of research and collaboration where the two disciplines overlap. This includes studying the chemistry of the natural space environment and objects in space, for example, moons, planets, and the space medium itself, as well as the materials and chemistry that are needed for the vehicles, propulsion, and systems that are used to support complex space missions. The workshop will feature brief presentations by our three distinguished speakers who are right here, followed by a round-table conversation and an open Q&A with the audience. So with that, let me hand you over to Alex, who will introduce the first speaker for today's panel.
All right. Thank you, Jacob. So my name is Alex Spacconi. I'm chair of chemistry and biochemistry department, and I'm delighted to introduce our first speaker, who is a great colleague of mine with whom we actually collaborate as well, is Dr. Peng. So let me just tell you a few words about Dr. Peng. He's currently a deputy chief scientist at the AFRL site at Kirtland, New Mexico, where he supports research across all the space vehicle directorate. He has received his undergraduate degree from University of Chicago in 1999, followed by a master's degree from Princeton University in 2002, and a PhD degree in chemistry from Princeton University in 2008. Tom has spent a lot of time working on a number of different projects across this area that we'll share today with you, some of these things. But I'm just going to highlight one area. He's been a principal investigator at the AFRL Atmosphere's Independent Biopropellant Consuming Additively Manufactured Solid Oxide Fuel Cells, abbreviated as SOFCs, for Assured On-Orbit Space Power Seeding for Disruptive Capabilities Program, SDCP. The DoD loves the abbreviations, as you will learn today. Where he led the team of researchers from the 3 AFRL directorates and a small business in developing novel SOFCs for use on space platforms. And so without further ado, Tom, it's great to have you here. Welcome.
Okay. Can you hear me okay? All right, so I don't know if I need to project. So thank you, UCLA, for hosting this event and giving me the opportunity to talk to you about the AFRL Space Vehicles Directorate. So here, I'm going to switch. Oh, next slide. All right. So a brief introduction. The Air Force Research Laboratory is the principal scientific technology and development center for the United States Air Force. To accomplish this mission, it principally drives a very diverse research portfolio, primarily across 9 technology directorates. So each of these directorates are going to have a vast research portfolio, and a lot of them are going to be doing things that are relevant to developing space technologies. For example, we have the Materials and Manufacturing Directorate, which is looking into developing on-orbit manufacturing capabilities. We have the Aerospace Systems Directorate, which is looking into developing different types of propellant. And then, of course, we have the Air Force Office of Scientific Research, which drives a lot of basic science. So what I'm here to talk to you about is the AFRL Space Vehicles Directorate. So the AFRL Space Vehicles Directorate, also known as AFRL-RV, is tasked with developing new space-based capabilities. And to do so, it leverages a team of approximately 545 scientists and engineers and annual funding of approximately $600 million. So all of this technology is desperately needed because if we take a look at the space ecosystem, it's rapidly changing. If we talk about just the 1950s and to the 1970s, space was effectively a domain which could only be accessed and utilized by the United States and Russia. Once we talk about in the 80s and to the 2000s, now we're starting to see some commercial space capabilities start to come into play, like GPS, the satellite radios, satellite television, satellite telephones. The fact that GPS was made available in that time, that's actually become a super critical resource where, I mean, right now when I talk to a lot of my students now, they say, like, how do I get someplace? I gotta use my GPS. It's really, really hard to navigate nowadays without access to this GPS technology. All of this stuff is starting to accelerate, and now we have a commercial space industry which is effectively now able to regularly send their own spacecraft, put them into orbit to drive commercial interests, and also they're able to supply satellite-based services at a commercially viable method. So all of this trend is expected to continue where it is anticipated in the future people are going to be starting to leverage the resources and the advantages in space in the same way that people go off to Hawaii to take a look at the beaches or dig in the Gulf of Mexico to get access to oil and gas. All right, so in response to this changing environment, the United States seeks to ensure that the space domain remains secure, stable, and accessible. It also wants to make sure that the United States and its allies will always be able to leverage the use of space to project power, to be able to employ power across all domains over the entire spectrum of conflict. The big thing is that this is actually a very, very big problem. And the reason why is because the United States has been in the space game for a very, very long time. And so consequently, through that time, it's built up a lot of habits when space was effectively only accessible by a few state actors. And what people could do in space was actually very, very limited. And so with this new changing environment, it's hard to break those old habits to accommodate what's happening now. So that goes into what the AFRL is up to. AFRL is trying to develop that technology so the United States has the technology and the capabilities needed to be able to thrive in the current and anticipated environment. And so these are our key mission areas. When we're talking about satellite communications and PNT, then AFRL has been putting a lot of resources into developing ways that we can be able to do position, navigation, and timing. We've been putting a lot of effort into developing wide and narrowband communications. We've been doing a lot to figure out how can we set up agile space capabilities aligned with user equipment. So what this is saying is that we want to make sure that people, wherever they are able to know where they are and they're able to communicate regardless of the environment they're in, the type of interference that they have, or the type of equipment. If they don't have the ideal equipment, they should still be able to access space resources. Missile warning and tactical ISR. So this type of area, this missile warning and tactical intelligence, surveillance, and reconnaissance, a lot of work there is focused on developing novel IR focal planes arrays and resilient sensor tech that's able to tolerate the abusive environments that are found in space. Space environment. So this is trying to figure out when we put a spacecraft into space, what does it have to deal with? This is so that we can inform spacecraft designers that this is the stuff that you need to be able to harden your equipment for. This is the type of corrosive environment that you're going to have to deal with. It's also trying to provide information to satellite operators. In particular, they want to know that, hey, if I have this space-based capability, when is something going to happen? And when that thing happens, is it going to help me? Is it going to hurt me? How is it going to affect my space capability? So a lot of work there in trying to figure out, all right, what's going on with the space environment? And then along those lines, we're thinking about, okay, we need to know that we want to understand the space environment. What can we measure about the space environment? How do we get that critical information? And then if we're trying to get that critical information, how do we get sensors that are able to collect that information? And if we don't have those sensors, how are we going to make those sensors? And if we have those sensors, how are we going to deploy them? All that lines up into the space environment thrust. Pervasive technologies. So pervasive technologies are going to be things that are in pretty much every single spacecraft. And so when we talk about that, what is that? That's going to be stuff like structures. We need to be able to deploy solar arrays. We need to be able to deploy antennas. It's going to be talking about power supplies. So when we're talking about, it's like we need that power to be able to run our space operations. So that's going to be batteries, photovoltaics. It's going to be fuel cells. We're talking about thermal control stuff because, as we know, as things get hot, when I get hot, I don't work as well. It's the same thing happens with equipment. When it gets too hot, it's not working as well. It's going to be talking about rad-hard electronics. We want to make sure that anything we send up into space, the computers, the processors that we have, it's going to be able to tolerate that space environment. So as a consequence, we'll have the computational abilities to be able to carry out the operations that you need. And then we're talking about operations. Then we're talking about things about saying like, okay, can we do rendezvous and proximity ops? Can we actually get spacecraft to work together? Can we get spacecraft to meet each other? Can we make sure that the spacecraft is going to go where we want it to go? Advanced space operations. That field is trying to cover the area where we're talking about things that we're trying to do things that haven't been done on spacecraft before. And so right now, that's going to be looking into being able to establish a capability so we can monitor what's going on in the cislunar space. It's looking to saying what type of protocols, what type of equipment, what type of firewalls we need to have to make sure that spacecraft now are cyber secure. And also, it's trying to look into saying, hey, when we have a spacecraft up in space, it's collecting a tremendous amount of data. we want to say that is there a way that we can actually process all that data so all the information that's in data is now in a bite-sized, user-friendly package that can be delivered in a timely way so people can make informed decisions in a timely manner. Small sat portfolio. The small sat portfolio is all about trying to make a spacecraft so we can test out a new idea, we can do some rapid prototyping, and also we can identify brand new technology. We can try out new technologies. Okay, excuse me. So why do we care about that? When we talk about a small satellite, its small profile means that it's easier to build, it's easier to deploy, and also when something goes wrong, because it's a small satellite, we can quickly sort out through everything and say, okay, yeah, this is what went wrong. And also, because it's small, there's less stuff that could possibly go wrong. Also, when we talk about a small satellite with a very, very focused mission, we can then scope down our mission to be focused enough that a single team can handle all aspects of it. That means that a single team can come up with an idea, they can come up with a spacecraft to be able to test that idea. They can figure out, okay, how am I going to build this spacecraft? They can actually build that spacecraft. They can get that spacecraft into orbit. Once it's in orbit, they can run all the on-orbit operations. They can do all the data collection and data processing. They can do the things that they can just because of the luck that they have that equipment. It's in that orbit. It's able to capitalize on something just fortuitous. So all of that, why is that important? By capitalizing and basically covering, oh, thank you very much. By capitalizing on every aspect of a flight experiment from its conception all the way to its end, then people get that hands-on know-how that's critically important to be able to conduct future space missions. Nuclear deterrence and operations. This is an eclectic field where effectively they're looking into things like inertial navigation, they're looking into be able to find ways to detect nuclear explosions, and they've been dabbling in hypersonics. And finally, we have a field of agile software operations. Agile software operations is all about trying to make user-friendly, intuitive software so that we can get people working with space systems without a lot of training. It's the kind of the idea of trying to make a nice GUI so that without getting a computer science degree or a space degree, you can start working with space technologies. And so all the work there is trying to design software that can be easily modified and updated to meet the specific mission requirements of a particular spacecraft. It's trying to define different types of libraries. It can facilitate software development. And it's also trying to find different types of software architectures that people can agree on so that we can know, like, okay, this is the basic idea. This is the way I can tailor things to meet what I need. So all of this R&D is aligned to enable the DoD, and particularly the Air Force, to be able to accomplish a couple of critical missions. So one of which is to be able to project combat power. It is a DoD lab, so we're trying to facilitate DoD activities. It wants to have the free flow of information. It wants to make sure that when spacecraft are up in space, they're able to go where they need to go, they're to do what they need to be able to do. It wants to have awareness of what's going on in the space domain. And also we want to establish space security so that people that have access to space equipment and space resources are limited to who should actually have those privileges. So with all of that different type of technology, I just wanted to talk a little bit about some of the big programs that we have going over at the Space Vehicles Directorate. So NTS-3 is an AFRL effort to develop a next generation satellite navigation technology. As we had talked, as I had mentioned before, satellite navigation is a very, very big deal. It's basically never been more pervasive. It's never become more important. We're counting on GPS to be able to manage our air traffic control, deploy farm equipment, deploy resources wherever it needs to be. The thing is, GPS has been around for decades now, and as you would expect, anything that's been around for decades is going to have its problems. And so with NTS-3, the big focus there is to say, hey, can we actually launch a spacecraft that can give us a reprogrammable navigation signal? And so by having that platform where we can reprogram the navigation signal, now we have a platform where we can rapidly test new waveforms or new approaches to broadcast that navigation signal. We also have a means to be able to quickly vet new approaches or techniques to be able to overcome spoofing or interference. Oracle Prime is a big effort to be able to try to be able to search and identify things in cislunar space. And so as we had talked about, with cislunar space, this is a totally new field. When we think about things in low Earth orbit, those are only going to be maybe up to 2,000 kilometers away. So if we think about the volume that could be, okay, we're talking about a sphere that extends out to 2,000 kilometers away. But when we're talking about the moon, we're talking about 380,000 kilometers away. So all of a sudden now, we're dealing with a massively increased volume. So we need to have new capabilities, to have new sensors to be able to track that giant increase in volume. Also, when we're dealing with things that are starting to approach the moon, things get a lot more complicated because we're not dealing with just the two-body problem anymore. The moon and the spacecraft and the Earth being this three-body problem, spacecraft in this particular region all starts to be able to move in very funny ways. And so as a consequence, there's a lot we need to be able to do to be able to effectively track the stuff that we know is up in the cislunar space, be able to detect if something new appears, and also be able to determine be able to search for things if we lost track of them. So if we take a look at the history of the AFRL, you can see that AFRL, Space Vehicle Directorate, has been part of a tremendous amount of critical technologies. I think that AFRL actually doesn't get as much credit as it deserves, but that I might be a little bit biased. When we talk about the key things I just want to point out is the ESPA ring. That's kind of the main thing that people are using right now. It allows multiple spacecraft to get into space with a single ride. That's become critical for all of the major experiments that are going on right now. We have ROSA, the Rollout Solar Array effort. That is a really big advance where we were able to integrate structures with the deployer. So in fact, instead of having a whole bunch of equipment, we just have this snap bracelet-like structure that automatically extends out our photovoltaic array to whatever we need. And we have the SPIDER program, the Space Solar Power Incremental Demonstrations and Research. That's looking into power beaming, where it's saying like, okay, can we actually use power beaming to take power that we get in space and effectively deliver it to wherever it's needed on Earth? So lots and lots of big efforts is being pushed by the AFRL. And so just to highlight a little bit of the work that I'm doing, this is the stuff that I've been pushing directly myself. One is reversible electroplating. This is work that I've been working on with the University of Mexico and Faraday Technology to apply electrochemical controls to be able to make a tunable optic. And so the basic idea here is that by applying electrochemical controls, we can define the transparency and the reflectivity of an electrodeposited mirror by using those electrochemical controls to define the thickness and the structure of the mirror. And so you can see with this particular technology, if we don't need a mirror anymore, we can just take it away. If we need a mirror with a different property, we can electrodeposit it on. If we have a damage to our mirror, we can take it off and then put something back on. By looking into this technology, we also set up a low-power manufacturing process. So this is something that I'm trying to explore to be able to enable more advanced on-orbit manufacturing capabilities. Reversible solid oxide fuel cell. So that was the long acronym that Alex had mentioned. The whole big idea here is that spacecraft and any really type of mobile system, we always wanted to be able to do more and be able to operate longer. I mean, that's the thing that comes out with every new smartphone. They say, this thing can do this much more, it will last this many hours. We want the exact thing with spacecraft. And so the thought is that, well, batteries are great, but pretty much they are limited. They pretty much we haven't seen very big increases in the amount of storage capacity from them. So I've been looking into fuels because with fuels, you really just can't match the amount of energy content inside a fuel. Even the very best batteries, they just can't match fuels. And so with a fuel cell, you can take that fuel, you can generate that electric power, and then moreover, with the fuel cell, you have stable voltage and stable current going through. So it's a lot smoother, and so as a consequence, you don't have to deal with this drop in voltage and current that comes with batteries. So you can design your electronics to be much more optimized to just that very stable current and very, very stable voltage. The problem with dealing with fuels is that once we use it, that's pretty much it. It's gone. And so a lot of the work that I'm working on right now, and this is with Oxyon Energy, University of Mexico, and Tennessee Tech, is to say, hey, can we develop some sort of technology that will allow us to take those combustion products and turn it back into fuel? So that is where there's a lot of work into the fuel cells and then the electrolysis cells. Boron cluster-based photonic cover glass coatings. So this is something that I've been working with professors, looking into with Professor Spagoini and Professor Karam here at UCLA. And so the idea here is that we need cover glass on our photovoltaics because, as mentioned before, space is a very corrosive environment. We got charged particles up there, we got corrosive atomic oxygen, we got gamma rays, lots of high energy photons. And so the thought is, okay, if we got to have all this high energy stuff that's coming at us, is there anything we can do to leverage that? Is there anything we can do to take advantage of that? Gamma radiation, high energy photons, UV light, that's a lot of energy. And so one of the thoughts is using the photonic molecules that Professor Spagoini and his team have come up with, is to say, let's take that UV light, very energetic, let's shift it down into the visible spectrum. And so as a consequence, we're now taking the energy and the power inside that UV regime and putting it down into the visible spectrum where the photovoltaic is already harvesting energy. And so by creating this type of coating, we now are able to expand what the photovoltaic is able to harvest without actually changing the underlying photovoltaic. And also, since we're dealing with boron clusters, the thought is, well, we got boron, we got atomic oxygen. If the two of those mix together, we got boroxide. So the thought is that if we have a polymer, we put enough of these boron clusters in them, they could form a protective boroxide-like thin film, some kind of protective layer. And if that is the case, now we're in a situation where polymers imbued with these type of boron clusters could react with the ambient conditions, doing chemistry in space, to create a protective film. And so now, if we're in a situation where we can take a polymer and make it treat like cover glass, that will massively decrease our solar panel manufacturing costs, because it's a lot cheaper to just be able to brush on a polymer or spin coat a polymer than it is to actually go through the delicate work of affixing a cover glass onto a photovoltaic. All right, so still here, nobody's left yet. So if you're interested in working on any of these projects that I've talked about, then there are a lot of opportunities for you to work with the AFRL. First off, we have the University NanoSat program. You can find out information out there. That's all about trying to look at what universities have, and whatever you have, they'll work with you to try to make it better. They'll try to get you through what type of classes you should take, you should make, what type of designing classes, talk about what type of equipment you need, and then get you to the point of that you can build a spacecraft. And then once you can build a spacecraft, if all things are going swimmingly, they'll help you get it onto orbit and carry out the operation. AFRL Scholars Program is our internship program. So that's where we invite basically people from high school, undergraduate, graduate, and all the way up to professional educators and graduate students, PhD candidates, to work with us in the summer. The DoD SMART program, that is a program that will pay for school, up to 5 years of schooling. So it will pay for both undergraduate and graduate school. It can be a mix of the both. And I think that's a particularly nice one because it'll pay for the full tuition. It'll still give you some healthcare benefits. It'll give you a book allowance. It'll give you time with the DoD researcher, so you get some mentorship, and you'll get a job with the DoD or government facility at the end of it. The one caveat with the SMART program is that for every number of years that you work or are supported by the SMART program, you have to work for the DoD. NDSEG. This is just money right out. So if you get this, it'll pay for 3 years of school. We hope that you do good science afterwards. NRC Research Fellowships. This will pay for postdocs and faculty fellows. So postdocs being anybody who's under 5 years from getting their PhD. Faculty fellows, somebody that's more than 5 years away. It'll pay for them to basically work on projects with the AFRL. One note, it's open to industry. So if you're not an academic, so we have some industry partners here, it'll help and pay for yourself as well. Summer Faculty Fellowship Program, SFFP. This is basically a program that will allow you apply for a topic, and you can bring an academic can bring themselves and their student to work over at the AFRL. Visiting Science Program, this is where AFRL visits you. So if there's an AFRL researcher that you want to work with, then this is the way that the AFRL will pay for the scientists to basically go to your research institution. Air Force Office of Scientific Research, mentioned before, they support basic basic research and education, find out all the opportunities over there. AFRL internship programs and scholarships, a whole big list of them, are all listed on this particular website. And then we're always good about setting up cooperative research agreement, educational partnership agreements, memorandums of understanding, so that we can start to collaborate and be able to share resources if it's of interest. And finally, we have the Small Business Innovation Research, SBIRs, and STTRs. Those are effectively programs that will pay for a university or a small business to work on something for a year, and then maybe up to 2 years, and then further on, just basically take that idea that you come into the lab and then turn it into a device. That's what the SBIR program is about. So if you're interested in any of this stuff, you may contact me. I'm happy to talk to you, and happy to talk to you at the reception afterwards about any of the stuff that was presented. And so with that, I'll throw it off to, oh, no questions? It's the next talk.
No, it's Tongva. We're switched around. Do you want to do Donna next?
Okay.
Okay, we'll do Donna next.
Oh, you can just go through the slides. Yeah.
I'll go through.
Oh, then we'd give away the punchline.
You want to give a talk?
Yeah.
Yeah. All right. Let me introduce Donna then.
You want to give that talk?
Okay.
All right.
All right. Before Donna gives a talk, I'm going to give a formal introduction.
Here's a clicker.
All right.
Is this for me? Or?
Yeah.
Yes, it's for
Thanks,
you.
Tom. And let's thank Tom again for a wonderful talk. Okay. So our next speaker in the program is Dr. Donna Speckman. Let me just tell you a few words about Donna. She is actually received her PhD from UCLA here, working with, for some of you in the audience might know the name, Professor Fred Hawthorne. And so, you know, obviously working on boron clusters can lead to an illustrious career in the aerospace industry. So Donna joined Aerospace Corporation in 1984, and her research career at Aerospace Corporation has covered a wide variety of projects involving, and I'm going to list a lot of cool things, spacecraft materials, including solar array degradation mechanisms, atomic oxygen interactions with satellite materials, metallic dendrite influenced failures in devices, quantum dot nanotechnology development, magnetic recording of storage materials development, microspheres for anti-static coatings, and chemical vapor deposition processes for metal and semiconductor films, to name a few. And so Dr. Speckman has won a number of prestigious awards for her accomplishments, including the NASA Engineering and Safety Center Group Achievement Award for her work on the International Space Station related to the coolants. She also received the Woman of the Year Award from the Aerospace Corporation, and she has also served as the technical co-chair of the AIAA Space Conference. And so with that, Donna, it's a great pleasure to have you back at UCLA anytime you come. So, yes. But I've never actually listened to your formal talk about the work you've done, so it's a really pleasure to hear.
I'll be talking a little bit about.
Thank you.
Is this on? Can everybody hear me? Yes. Okay, good. All right, so I'm going to talk a little bit about work that's being done at the Aerospace Corporation. At the end, we can talk about, I might have time to talk about some of the cool projects. If we don't talk about them here, we can talk about them at the reception. Am I getting feedback? All right, so, you know, AFRL's Air Force Research Laboratory. Who in the world is the Aerospace Corporation? Well, they're just down the street in El Segundo. The Aerospace Corporation was established in 1960 as a nonprofit. It was actually established by Congress and the Air Force as a scientific and technical planning and management corporation for missile space programs. The space programs were taking off mainly in terms of military defense. So Aerospace actually took over Space Technology Labs, STL, which was a subsidiary, if you will, of TRW. And the Congress and the Air Force said, it looks bad that people who are bidding on government contracts have the science technology labs which are evaluating these technologies, like having an input. It looks like a conflict of interest. So let's spin off a nonprofit, has nothing to do with TRW. Our goal, our customer is strictly the government. And that's our focus, that's who we support. We provide, so now we operate a federally funded research and development center. There are many of those, Oak Ridge National Labs and these different things, different places. We are the space arm of the FFRDCs. We provide leadership and expertise for science and technology efforts to national space. We act as a trusted strategic partner, so anything that is shared on projects that we work on, we are trusted with not spreading that information to places it shouldn't be, to competitors if we're working with a contractor. We keep our focus on just having our customers achieve their successful satellite programs. We have, so we're unbiased. That's our big thing. And we work across multiple organizations. We work across multiple programs, so we have insight into different programs that might otherwise be stovepiped. If there's a problem with a solar array in one program, they're not talking to another program. But if we're working the issue, we can say, hey, there's something wrong with that technology. We can help our customer not have those same issues on other programs. So we can talk science in support of customers across multiple programs. And we have since expanded from just being military government, DoD. We also do civil work. That was part of my NASA. I've done some NASA projects, working for NASA, working for aerospace, but working on NASA programs, commercial space like SpaceX and the like. So anything involving space we're involved in, and also intelligence community satellite programs, which I won't be able to talk about today. But what that allows is a lot of cool research activities at the Aerospace Corporation. In fact, our original CEO was Dr. Ivan Getting. He was an astrophysicist, I think MIT, could have been Harvard. But he firmly believed if you're going to be advising the military or the government on what they should be investing in and the technologies they should be investing in, you better have some solid research to back up what you say. So when aerospace started off with 5 research laboratories, and that has since expanded. So you've already kind of heard this, but we'll just run through it really fast. The space domain is getting more and more critical as more and more players are involved, more and more countries are shooting up satellites, universities are shooting up small sats, everybody's shooting stuff up into space. All right, so there's a whole variety of applications for those satellites. So space industry includes the civil, so the NASA, NOAA types of things, like the Joint Polar Satellite, Mars Insight Lander. We have commercial, Iridium, Starlink, and intelligence community. We can't talk about those. Or DoD systems, GPS you heard about. In fact, little aside, the GPS concept originated with an aerospace engineer. We started with the Air Force. We established a GPS program office. Aerospace got the Collier Award for its, so we basically worked hand in hand with the Air Force to develop the GPS system. So that's an Aerospace Air Force joint effort. So it was called, what was it called? Anyway, I forgot. It had some numbers in a letter initially, and then it became GPS. So we have communication satellites that, they have to work. We have space weather satellites and a variety of military-based satellites that sometimes have commercial applications. The consumer gets to use them as well. All right, so chemistry. All of you probably have different chemistry backgrounds. There's probably a place for you working in the space domain. So chemistry is involved in all aspects of the space itself, understanding the space environment, spacecraft, and launch. If you're talking about the satellite itself, it's got a function. You've got structures. You've got components. You've got electronic components. You need power. You've got payloads, whether they be telescopes or communications. You have to survive in the space environment. All of those things say what do you need to do to have your satellite operate in space and serve its purpose? So you've got basic research for new materials and new power systems, et cetera, et cetera. You have to test them before you launch them. Nothing worse than launching something and it doesn't work, which does happen even with testing. And anomaly investigations, that's when things don't work. Hopefully you catch those things when they're on the ground and solve the problem. Sometimes you don't find them until after the launch has happened. So there's a little detective work. That's kind of an interesting part of the job, too. It's like, what went wrong? Can we figure out what went wrong? Can we fix it? Launch vehicles. You've got to launch the thing before it can go up into orbit and do its mission. So you've got to be able to launch heavy and light satellites. You've got to have different kinds of batteries for your launch vehicle versus your satellite. And of course, the materials have to sustain that launch. And your fairings have to stay intact and keep your satellite protected and not get it all dirty while it's being launched as it's shaking like this. And then, of course, space exploration, which, of course, NASA does a lot of. So science experiments, if you're a chemist, you can help with that. I actually had the nice opportunity of being a proposal evaluator for some of the Mars Laboratory and Mars Scout programs where I evaluated instrumentation. So it was really cool to see what people were proposing and to see what actually got selected for the missions, which was cool. So you've got to interpret data, and someone's got to manage those programs. All right, so again, Tom covered some of this. You've got a lot of different technologies in satellites and launch space domain. You've got the specialized payloads, whether it be a focal plane array or some kind of special communications or special cameras looking at stuff, or you've got your weather, you're getting information about weather or ground. NASA does, Earth, ground, satellite to Earth studies. You've got to analyze data. You've got to survive once you're in space. We'll talk a bit about that. There's a lot of hazards in the space environment. You've got to have the equipment to do the analysis you want, sensors and telescopes and cameras. You've got to launch successfully. Luckily, we saw a really nice example of a successful launch recently. You've got to power the satellite once it's up there. You've got to be able to orient it and move it around, maybe do orbit-to-orbit raising. You can, so that also involves some in-space propulsion. Tom also talked about mechanisms. You have things that move, moving mechanical parts. And if you have sensors that are imaging the Earth, getting information, you want to make sure that those sensors are working properly. So you have to periodically calibrate them, and you can do that through ground truth measurements. So you have the satellite look at something that you want to analyze. You have your ground system look at the same point and say, are we getting the same results? So there's a lot of different things that make space chemistry interesting. So where's chemistry used? Materials, a lot of materials work. Research and application, you've got ceramics and adhesives and polymers and composites and specialty coatings. There's all kinds of cool stuff that development, testing, evaluation, what are the degradations, how well will it last, how well will your materials last in space, how do they degrade, is that going to be a bad thing, is it an okay thing? Additive manufacturing, laser micromachining, we make some interesting little parts, both with additive manufacturing and laser micromachining, and developing new analytical techniques so that you can evaluate these components that you're developing and make sure they're suitable for their applications for space. You've got to survive the spacecraft environment. You've got radiation, thermal cycling, high intensity UV, your solar panels, you can have electrostatic discharge events if you don't have conductive enough materials on the exterior. You can blow out your solar array, blow out your microelectronics, things you don't really consider about. And if you're in low Earth orbit, atomic oxygen, very highly reactive, radical, that's very aggressively attacks materials. You've got power, if you're in the sun, you need your solar rays to give you power. If you're in eclipse, you need your batteries to give you power. You need to have propulsion, both to launch and to orbital maneuvers when you're in space, and of course, all of your payload, different types of payloads. Chemistry is involved in all of those. So I thought I'd just give a little sampling of some of the different types of chemistry-related research we do at the Aerospace Corporation. It's just a smattering because we have lots of cool stuff. I like the non-destructive evaluation folks because they're always looking at things that are broken. and one of the things, oops, did it break? Sometimes you're moving something that is ready for flight and something goes wrong. In this case, this fell over. Is it broken? It's all ready to be loaded into a fairing and launched. Is it broken? You can't take it apart to evaluate it. That will cost you so much money in terms of repairing it, looking at it. Sometimes these parts have been in storage to build this thing, and nobody makes them anymore. So you don't even necessarily have the parts to repair it. So that's where the NDE folks come in. They use non-destructive evaluation techniques to look for problems like cracks and voids. And here's a composite overwrap pressure vessel that was hit with a hammer. You can't see that. But in shearography, you can see where the damage occurs. And some of the techniques that are developed at Aerospace, we actually get patents on them and then transfer the technology, because we're nonprofit. We don't make anything. We don't manufacture anything. We don't make a profit. But in fact, this flash thermography technique was then handed over to the contractors so they could do analysis of their solar arrays and look for things like voids where the adhesive did not go all uniformly where it needed to be. So constantly developing techniques and applying them, or developing portable techniques where you can take to a launch site, do your evaluation at the launch site. So that's a cool group. I think their stuff is really fun. I think it all should be fun. Whatever you're going to do for the next 40 years or so should be fun. So space environment testing, another cool thing. Again, the space environment, you've got electrons, you've got protons, you've got UV, you've got temperature cycling, you've got atomic oxygen. All these things can screw up materials that look beautiful on the ground. So here we have the coated Tedlar. That's a material. It's white. It's supposed to be white. It's supposed to be, part of your thermal coolant, nice and reflective. Keep your satellite cool. Well, there's Tedlar over here after a year of electron environment in the in geosynchronous orbit. Not so reflective. Not so. It's not as cooling. In fact, it's absorbing. And a 5 year, or 3 years rather, of geoelectrons, it's actually crumbling. So we have several environmental effects test chambers where we actually expose materials that are being considered for use, and we can bombard them with all kinds of stuff. We also have a gamma source. We can bombard it with gamma radiation, protons, electrons, and simulate the environment. So if someone calculates, if you have a 5-year mission in geo, what's the electron profile you're going to see? What's the proton profile you're going to see? And tailor it to the environment you're going to be in and see how well your materials hold up. This kind of was close because I work with photovoltaics. This is an example of solar cell cover glasses. So on your solar cell, you've got to have a cover glass. It protects the solar cell from electrons penetrating and ruining your solar cell. And you put an anti-reflective coating on the top of that, so you can reflect off heat that you don't want to absorb just what you do need. So there was the company that was making the cover glasses and the coatings had to shut down their old machine, their coating machine, and build up a new one. They either had to move to a new location or whatever. So they rebuilt the machine and then started coating their cover glasses using the same recipe they'd always used that had already been vetted as being good stuff, no problem. And Aerospace, one of our aerospace people said, I think we should test the new material. Yeah, it's supposed to be the same, but let's put it in the Space Environmental Effects Test Chamber and see, let's make sure it's working. This right here is the old cover glass, nice and clear. These are cover glass, coated cover glass from the same recipe in the new chamber. Something isn't right. And if you have brown cover glass, the cell's not getting all of the energy from the sun that it needs, and so your power is going to be limited. So it's one of these things you want to test, even if you think you know what's going on, you test, because something, I'm not sure anyone ever figured out what exactly went wrong, but these are the things that pop up when you start doing testing. Will my stuff last? This is kind of new. Aerospace just got a patent on a nice, inexpensive, low-cost, replicated optic, a way to manufacture basically mirrors that are made out of polymers. So you don't have to actually make a metal mirror and grind it and polish it to the right optical qualities. You can make these lightweight, replicated mirrors that have the same optical properties as a nice polished telescope. So again, you save time, you save weight, you save all this preparation work. So there's some cool polymer stuff being done at Aerospace. We do have additive manufacturing capabilities. We can do 3D printing of metals, plastics, you name it. The thing about using additive manufacturing where you're building up metals layer by layer and making, kind of cool, unique structures is that the materials are not necessarily, they don't necessarily have the same properties as a bulk metal. The grains may be different, the performance may be different. So Aerospace has nice materials lab that says you can build up, you can make your structure, you can analyze the microstructure of the metal to see, is it similar to a bulk, what we're used to? We can't just assume it's the same as if you made something out of a piece of, a solid piece of metal. The bulk may be properties may be different. We measure, we can test the material properties, and then we can test its performance. So we have these new cool tools, but you can't, just because you can make it doesn't mean it's going to perform the way you need it to, because there can be differences at the microstructural level that's going to affect its performance. So we have some cool techniques and some cool research going on in that area. Chemical propulsion, we heard a bit about this too. That's another cool thing because things blow up and ignite. And for old-fashioned chemists who like to see things burn and explode, it's perfect. So we're developing green propellants. We have a test facility. It's a separate building away from all the other buildings. And an alarm goes off if something goes wrong, but they test all these high-energy materials. So we do rocket testing, we do laser diagnostics of the plumes that are generated from the various propellants. We can study the combustion kinetics, and we can use 3D prototyping, rapid prototyping, to make new grain structures that might burn more efficiently and study those. So we have a whole program in propulsion chemistry. Chemical propulsion. We also have a huge effort in electric propulsion. We have a test facility, electron propulsion test facility, where we test virtually, I think we've tested probably every ion thruster in the world. People bring them in and we test them. So we had a smaller version, which was the EP2. Now we have the EP3. It's even bigger and fancier and cool. And we also have a diagnostic chamber off of the EP3, and this tests for electromagnetic interference. So when you fire your ion thruster, that can interfere with your comm signals. So you may, and if it does, if you get a lot of interference signals from your thruster, you might have to adjust your communications when you do your comm. Like fire the thruster, no comm during that time. Once it's shut off, you can send communication. So those kinds of things are important. And so we do a lot of analysis with electric propulsion. And then we have batteries and solar arrays. That's the group that I'm in right now. And again, always looking at future technologies, improved technologies, solar arrays that are lighter in weight or have more junctions. When I started off, they were single junction. There were silicon cells, then there was single junction gallium arsenide, and now we're up to like 5, 6 junction cells, and these little, very, very thin solar cells as well. But how do they behave? The more junctions you get in the cell, the more different wavelengths of the light you're going to be absorbing. You need a simulator, something that simulates the space environment, and as you get more and more junctions, you have to have more and more zones of light hitting your sample so that you get something that's realistic. We also do a lot of battery lifetime testing, because these things have to go up and do tens of thousands of cycles when they're on orbit. And also thermal runaway studies, another fun thing. That would be out in the parking lot. But we've also done impact studies where we puncture a cell and watch it blow up, basically. So what can you do to avoid that? Trying to understand what causes those phenomena. And this is the last thing I'm going to give any little detail on. Another one I like. As you heard about the ROSA array, that's a rollout solar array. That has a mechanical thing that has to move. Your reaction wheels that spin around and keep your satellite pointing in the right direction, that has bearings. Those are things that have moving parts and metal parts, metal to metal parts. Tribology is the study of friction, metal to metal parts, wear and lubrication. So we have a robust research group that studies both solid and liquid lubricants. We study how things degrade with friction. So we have reaction wheel bearing testers and such, that because if your reaction wheel galls or gets stuck, there's no Jiffy Lube up there that you can take your satellite to, and they can put a little more lubricant in it. You got to make sure when you launch that thing, that lubricant's going to last, and it's going to keep everything flowing, moving smoothly for the life of the satellite, or at least the life of the mission. So we have, ultra-high vacuum instrumentation to study lubricants and their decay. We've got the bearing tester. We've got various things that test both the friction, that study the chemistry of degradation of the different lubricants, because anything that has a part that moves, you want to make sure it can move when you need it to move. Otherwise, again, you can't roll out your solar array. You have no power. You're dead. Nothing to charge the battery, and you're kind of done. You got a big piece of junk up there. All right, so tons of other stuff here. Tom also mentioned small sats. Aerospace actually got started, the first small sats, not a CubeSat. We developed the first small sat. It was two little things that looked like, for those of you that remember VHS, they looked like VHS containers. And that was the satellite. That was a DARPA Aerospace Rockwell International joint project. And this person worked on the original DARPA satellite. And they actually had to connect these two little satellites with a long cable because the cross-section was so small you couldn't visualize. The radar cross-section was too small to visualize from the ground, so they had to connect the two little tiny satellites, which was pretty cool. We have, again, fiber optics. We do miniaturized fiber optic communications that are put on CubeSat. We have a huge CubeSat program as well, small sat program. And again, we do a lot of testing of new technologies, some that we develop here. We evaluate new solar cell technologies, fly those up, get feedback. How are they behaving? We have a whole facility for integrated optical tests on Mount Wilson, a variety of telescopes at the Aerospace Corporation, some rocket testing done out in the desert. So we have a lot of cool things. Polymers, remote sensing, hyperspectral imaging. That was another cool one. Back in '91, if y'all remember the World Trade Center collision, catastrophe, Aerospace was actually tasked with bringing out a hyperspectral imager to do a fly, which we had that fit into an Otter 2 plane, small plane, and do a flyover collecting data over the World Trade Center area because they were looking for Freon, so looking for the chemical signatures for Freon. And the fear was if the air conditioning systems in the buildings had broken open, they could react with the burning insulation and form some really toxic materials. So before sending the firefighters into perhaps a poisonous atmosphere, our guys went over there and scanned and said, no, there's no Freon, everything looks good. You can send your folks in. So there's a lot of cool stuff that's gone on at our company throughout the year. Lots of cool, exciting activities. So there's always, you've heard, the future is always evolving. We always need more people, more evaluations. That's our atomic clock test bed for position, navigation, and timing, like GPS. We're always evaluating new clock technology. We've got just new applications all the time. We're always looking to, of course, you always want it all. I want to reduce the cost. I want to reduce the weight. I want to reduce the size, but I want it to work better. So that's always the goal. You can never have it. I don't know if you remember better, cheaper, faster. You can get 2 of those. I can never get all 3. But everyone's still shooting for that holy grail, always improving. One thing also that hasn't been mentioned thus far is as everybody keeps shooting more satellites up into space, it's getting very crowded up there. So some of y'all are going to have to come up with some really cool technology to start cleaning up the debris because it's becoming dangerous to launch things and to operate. And there's little pieces of debris that if they hit your satellite, you're dead. All right, so that's about it. Tom gave you a lot more things to look at if you're looking for research ideas. Look for technology roadmaps. You can Google these things, technology needs statements, calls for proposals. There's NASA ones, there's AFRL, there's other government grants, and so that's about it. Those are things you can do on your own. So I'm not going to talk about, we can talk about anything I've done later. I'd like to thank everybody for your attention, and if you have any questions, I think it's an exciting, very important genre. The space domain, getting to work in the space domain will never be boring. And it's becoming increasingly more important. Thank you.
We truly, the complexity that goes into designing these space missions is just mind-boggling. I'm just always reminded and refreshed by that. Thank you so much for that. So I'd like to introduce our third and final speaker for today. This is Tomče Runčevski. Tom was born in Macedonia, where he finished his undergraduate studies in chemistry in 2011. He did his PhD at the Max Planck Institute, MPI, for solid-state research in Stuttgart, Germany, with Professor Robert E. Dinnebier, where he graduated in 2014 with honors. After a one-year postdoctoral stay at the MPI, he joined UC Berkeley and Lawrence Berkeley National Labs in 2015 as a postdoctoral researcher with Professor Jeffrey R. Long. In 2018, he started his independent career at the Southern Methodist University as an assistant professor of chemistry. In 2024, this year, he received an accelerated promotion to associate professor with tenure. Congratulations. He received the Otto Hahn Medal, the NSF Career Award, ACS PRF Award, Stephenson Award, and Sam Taylor Fellowship, among others. So very highly recognized, and we're very fortunate to have him. Currently, he serves as a topic editor at the ACS journal, Crystal Growth and Design. So Tom, the floor is yours.
Does this work? My voice carries, so if this doesn't work, is it okay? Perfect. Thank you so much for the invitation. It is very challenging to give a talk coming from a university, from a very small university that is, after the Aerospace and the Aerospace Corporation. But I will try to keep you engaged, me and my two grad students. Before I introduce you to the topic of my presentation today, Titans in a Jar, very brief introduction of what we do as a group. We have three very distinct areas of research. Work with hybrid materials, trying to look at solid materials that have both organic and inorganic counterparts. And now this one, the solid formulation, is actually quite interesting for this room, because I just learned that this room was made possible by a patent from a drug, and just today, few hours ago, I was going back and forth with a patent office of the United States fighting to get one of our drugs patented. So it's very motivating to hear what kind of success can a patent bring. And that brings me to what we will talk about today: Titans in a Jar and our research in space chemistry. Today I will talk about first why Titan, why I'm interested, or why we choose this place in our solar system. I will present one case study of what we do, but then I will talk more about the research framework of how we approach this research, move to conclusion, and I will talk about future. First of all, how do we know about Titan? Well, we do know because the Cassini-Huygens mission, which concluded not long ago, revealed that Saturn and its moons are an extremely interesting place in our solar system. And it's not just me that thinks so, but NASA thinks so too. And they will follow up with another mission to Titan, not just to Saturn and all of the moons, but specifically to Titan. This new mission is called Dragonfly. It will take off, 1 year later now, 2028, and it should arrive on Titan in 2023. It will stay on Titan for over 3 months, and it will explore the surface. So why Titan? Because it is one of the few places in our solar system that has a very dense atmosphere. This atmosphere is made of nitrogen and methane. So fueled by the sun, also Saturn's magnetosphere, nitrogen and methane react. They react and they build a lot of different molecules. They build ethane, methane, propane, butane, and so on. On the surface conditions of Titan, 93 Kelvin and 1.45 atmosphere. Nitrogen and methane, as I said, they will make the atmosphere. Ethane, methane, and propane make up the lakes, and they will be in a liquid state, but everything else would be solid. I'm 1000% sure that if we walk away from this room and go to the first lab, we will find benzene, for example. And benzene for you and I might be just a chemical, but on Saturn it's actually a mineral. So my research group is trying to understand a little bit better about this space mineralogy, and together with colleagues from NASA, we recently, not that recently now, 3 years ago, we published a summary of this and the inceptions of this research field about minerals on Titan and how they would look like. Before I go and talk about Titan, I just want to focus about the big picture when it comes to our solar system. The moon, which was our focus in the 60s, it is composed of, and I say common surface minerals, oxides, magnetic rocks, and so on. So is Mars. That is the center of our attention today. Mars is a pretty inorganic body, and we are hearing about Mars over and over with the Curiosity rover. But Titan is special. Unlike the moon, unlike Mars, and unlike any other place of our solar system, Titan is made of organic molecules. Not only of organic molecules, but solid-state organic molecules. And for those of you who are chemists, that you do know that organic chemistry is very niche when it comes to the small molecule science, but when it comes to solid-state organic chemistry, that is even more niche. We do not understand some of the most fundamental features of the smallest organic molecules, and today I will talk about that. But before I talk about how little we know about the smallest organic molecules, I just want to introduce you to this concept of Titan in a jar. Back in the day before I started my independent career, I was watching Jurassic Park, as we all do, and Dr. Grant said that there are two types of children: those who want to be astronauts and explore space, and those who want to be astronomers and stay on Earth and explore the space from Earth. But I would argue that I wanted to be a third type of kid that explores the space not looking up, but looking down. And the Titan in the jar is exactly what it sounds. Our goal is to reproduce all of the models of processes that go on Titan in a capillary, in a well-controlled environment, and mimic what is going on Titan. For example, do we say that there is an atmosphere? Sure, we can make an atmosphere. We will put nitrogen. Do we say there are liquids? Sure, we can do that. We are putting ethane. It will condense. We will get the lake. Do we have evaporation and minerals that would form after that evaporation? Sure, we can do that. We'll pull vacuum. We will get it done. When I say this, I don't really mean us in just one lab. My group works with a couple of places around the globe, and all of the experiments that I will present have been done, well, here is Dallas. I haven't put a star on it, but they have been done in large-scale facilities. For example, we do work with high-pressure studies with Brookhaven National Lab, with NSLS-2. We have excellent collaboration with NIST, in which we do a lot of neutron diffraction, but more importantly, inelastic neutron scattering to learn a little bit more about the dynamics. We recently started working with DESI in Germany, in Hamburg, working with pair distribution function in total scattering. We work with Oak Ridge quite a lot recently, working on a vibrational neutron spectroscopy, a super cool method for those of you that are chemists, material scientists. And finally, Argonne National Lab. Our first paper was with Argonne, so that's a pretty special place to me. So all of these places together are the places where we put our jar. And once we put our jar there, we try to learn something about Titan, but not just about Titan. We want to learn something about the very nature of our universe here on Earth as well. I will present one case study, and that case study would be on benzene and acetonitrile. There are two reasons why I chose this study. One, both of them are important for Titan. Benzene has been identified on Titan. Acetonitrile has been only tentatively identified on Titan, and I will talk about it in a second. But before that, the other reason why I chose to speak about these two molecules is what I said before. We don't know, there is so little that we know about the simplest organic molecules. Benzene and acetonitrile are present in every lab in space. Benzene is the most common solvent, acetonitrile is a second. To learn something new about these two molecules in 2024, it is astonishing. And it is my belief that for the organic chemists, before we go to larger molecules, we should really first go step back and really learn something about the smallest organic molecules. But then now I will move to why this is important for Titan. As I said, benzene has been identified. looking at the spectroscopic signature, acetonitrile has been tentatively identified. When I say tentatively, the discussion there is a small shift in the spectroscopic signature. And for people that are not organic chemists or not chemists, they will say, well, we have acetonitrile in our lab. We can measure the spectral signature and compare it and see if we see it in space or not. That does not work that way. And that's the reason why we do need more organic chemists in this field. Acetonitrile, benzene, all of these materials, not only that they can exist as different polymorphs, they can exist as co-crystals, salts, clatrates. They can form different solid forms. All of those solid forms have different spectral signature. That misshift may not be a reason that acetonitrile is not on Titan. It might be that acetonitrile is not in the form that has been matched with what we have in the library on Earth. So our first step in my research group is to go and fill those gaps. We understand that Titan is not composed of only one molecule. Titan is a mixture, and this is exactly what we try to do. Look at mixtures. It was our surprise that no one looked at the mixture of benzene and acetonitrile, and no one had constructed the phase diagram in great detail. Using differential scanning colorimetry, we constructed this phase diagram. And for those of you who remember phase diagrams, this is more complicated than a normal phase diagram. We do know that there is so much more than just the simple eutectics. To understand what is going on in great detail, we need to follow this phase diagram along those isoplates. We can do that with many techniques. We chose to go and do it with the Argonne National Lab and with powder X-ray diffraction. We collected all of those data. I'm talking about thousands of patterns, not just one. And all of those thousands of patterns have been analyzed in great detail. And we discovered, for example, in this part, that we are matching exactly what we are seeing with colorimetry. Here we have liquid. Here we have one phase, which is benzene. But here we discovered something completely different. We discovered two solid phases. One solid phase was benzene, but the second solid phase was unknown. And this is what I say, this is so surprising to us, because when I started this research, very naively I thought that everything will be known. No, we discovered a new phase of acetonitrile and benzene, the two most common organic solvents, just a few years ago. It was extremely difficult to get it solved because we were talking about a mixture, we were talking about cryogenic conditions, we were talking about powder diffraction. So for those of you who are not experts in the field, powder diffraction is the devil when it comes to analysis of data, but this is an important structure. Now, if we combine colorimetry with powder diffraction in this case, we have a full mapping of this phase diagram, and now we can learn about all of these phases that can be present on Titan, and we can really learn about it. We can also use this knowledge to look in the past of Titan. So here we do know that, well, we obviously know that there are huge lakes of ethane on Titan, and we now know that this mineral that I presented, acetonitrile and ethane forms, and benzene forms a co-crystal. This is just a hypothetical application. Our idea is the following. If, for example, so in the future, Dragonfly or another rover would detect this co-crystal in a pure form, it's one thing. But if this co-crystal comes in touch with ethane, because of how similar ethane and acetonitrile are, we are building a ternary phase. So basically, we can use this co-crystal in the future, potentially, as a marker for the past presence of a lake on a specific site on Titan. And I think that this is quite cool to use basic fundamental solid-state chemistry to look in the past of a planetary body. If you want to learn a little bit more about this, we published this paper a few years ago in ChemCom, and this is the paper that was about the overall field of organic minerals. This also was on the cover of ChemCom, and this is not how Dragonfly would look like. It's just, I had to. Moving forward, this is the big picture that I was saying. Benzene and acetonitrile are definitely not the two molecules. Titan is a world. It's not one isolated project. This is a phases diagram that we are continuing and we are studying right in the moment. And we right now switch to ternary phase diagrams, and we're trying step by step to build the complexity. But another big picture question is structure. Compositional diversity is one thing. Structural diversity is something completely different. When we talk about structure, depending on what kind of chemist you are, you're thinking of different structure. In my group, we are trying to attack this structure in different ways. We are, of course, using infrared spectroscopy and Raman spectroscopy to learn about the motion of molecules. It is extremely important for remote sensing, but more importantly for the structure of materials themselves. We do a bunch of calculations to really understand how the vibrational spectra look like, and we also do two-dimensional analysis to look deeply in the structure, especially in the lattice motions. Recently, and we just published 2 papers with Oak Ridge National Lab that will look with vibrational neutron spectroscopy, which is something like 1,000 times cooler version of Raman, unfortunately limited to just few places in the world. Besides of spectroscopy, we do a lot of structure. I presented acetylnitrile and benzene as a co-crystal. These are polymorphs which are unpublished, hopefully soon to be published, of propionitrile, another common solvent, and it is a great honor to publish something new about propionitrile in 2024, well, 2025, because let's be honest, it will take us some time to get it together. When it comes to structure, nothing is static. We, as crystallographers, would solve a structure and say, this is a structure. No, it's not. Things are moving inside, and there is disorder. We try to understand the disorder quite well. We do work with peer distribution function analysis quite a lot to really understand static but also dynamic disorder. When it comes to dynamic disorder, this is where neutrons come to play. I know that UCLA has some excellent research on NMR for this type of purposes. Our method of choice is neutron scattering, just because we are more familiar with that method. And for example, we can see, and I will not bother you with the details, but we can see that propionitrile does rotate and is dynamically disordered just using this methods in the solid. We also do a lot of preferred orientation growth, which is important for a bunch of different phenomena on Titan that I can talk in great detail later. We also do a thermal expansion just to understand how these materials will crack on the surface and so on. I will conclude. I will talk a little bit more, but for now I will conclude with, instead of giving a full conclusion about Titan, I will say Titan is a world, and it will not stop here. Chemists want to do a very well-defined research, get it done, and move on, but we cannot do that with Titan. It is, as I say, a world. And if you're bored with reading scientific papers, there are a couple of news outlets that featured our work, so that is arguably a much better place to learn about our work. But before I finish, I want to just talk about a little bit about the future and our big picture in my research group. Titan in a jar is only one project that we are working on, but this framework that we develop, it is absolutely not limited on Titan. We actually just started a similar project, which is the colors of Io, in which we're looking at this type of phase diagram to understand how and why Io is so colorful. There's also tints of blue, from blue to yellow, and we don't need to go to space to apply this framework. We absolutely can do that here on Earth, looking at petroleum, which is very similar to Titan, actually. Moreover, what we learn from this research, it can be applied to chemistry, and what we do now, we are trying to everything that we learned about Titan to apply it in synthesis of materials that potentially can have very interesting applications. I will present one sliver of this idea. We know that if we have benzene and if we subject it to very high pressure, we'll get graphene after reduction. We know that if we have acetylnitrile, if we subject it to pressure, we are getting trimers and eventually something like similar to diamond. But what will happen if we subject it to pressure, this newly discovered co-crystal by us? We don't know. Functional graphene, porous graphene, these are extremely interesting materials that we don't know how they will structurally look like. So our goal here is to basically, whatever we'll learn about Titan, just to take it and try to do very cool chemistry and potentially discover materials that can make a full circle and be used in space explorations, especially if we discover, for example, nitrogen functionalized graphene, which would be super cool for its application. And finally, we are interested in life as we don't know it. I personally would never work in origins of life because it's a very contentious part of research. But what we try to work is not origins of life as we know it, origins of life as we might not know it. Titan, it is made of organic molecules. It is believed that, well, it's not believed, people do believe that for life we need a very strong bonding, covalent bonding. And on Titan there is not enough energy to make and break bonds. That is true. However, the basin on Titan, the thermal energy is very low. So our belief is that on Titan and similar environments, what we have here as a covalent bond takes the role of hydrogen bonding, London forces, those weak interactions. So we try to understand how those weak interactions may give rise to life as we don't know it. And well, this is actually the real conclusion of my talk. And I will go back what I said, Titan is a world. And I do hope that there will be more scientists that will join us in these explorations. And this is my small research group. And these are our collaborators, which without them, this research wouldn't be possible. Thanks to them, and thank you so much for your attention.
Fascinating how much cool chemistry exists out there, even in our near solar system that offers so many different opportunities for research and exploration. So we are running a little bit behind schedule, as some of you may have noticed. So I think what we'll do is just an abbreviated Q&A. We'll maybe run just a few minutes into our reception time, but since we have our three distinguished speakers and such a great opportunity to probe their minds, we thought we'd do a Q&A, and we'll just pull up some of the chairs now. If we could ask our speakers to join us at the front here.
Yeah.
One more question quickly is, you guys are familiar with LDEF, Long Duration Experimental Facility? Lots of information about something that's been in space for a long, long time. I think it's roughly 5 years. Memory serves. Again, I didn't see any of that data entering into your research. Is that being used?
We are using that.
You are using
Yes. So yes.
Maybe you can repeat the question.
So the question was, what about LDEF, which is long duration environmental, whatever. Basically, you put materials up on the space station and expose them either to the high velocity side, and you put some samples on the side that's sort of protected, and you see how they behave. So we've actually sent some samples up, some solar cells, materials, paints, various materials. So we did a lot of the atomic oxygen information came from LDEF and similar things. LDEF stopped. LDEF moved into other. There were different. I forgot the name of the platform, the little suitcases that we'd send up. So there were still. LDEF was really long duration. So you saw a lot of micrometeorite damage and all kinds of stuff. And in fact, one of our atomic oxygen experts wrote a huge paper on AO, atomic oxygen effects. Wayne Stuckey, who has since passed away, unfortunately. But there used to be other suitcases of samples we'd send up. We haven't had, that one hasn't gone up in a long time, really probably since the shuttle. Probably the shuttle. So the shuttle could bring things up and bring them back in a reasonable amount of time. Some things would get stuck up there. Usually it was up there for a year. Sometimes if you didn't have a shuttle launch, then they'd be up there for 2 years and you could get more data. But nothing as extensive as the LDEF.
As you guys know, that was marooned because of Challenger. We couldn't recover them. The batteries ran out, the power was gone, so basically it was just an experiment, a dead thing in space, but we did bring it down, and micrometeorite information was pretty valuable.
Yeah, and that of course is getting to be more of an issue as we have more junk up there. And more little bits and pieces, and when the Chinese ASAT thing happened, just a spray of garbage. But yeah, it's a big issue.
So I would just jump in to say that I think all that stuff is still being done aggressively. It's just that it's now incorporated into a bigger experiment with different objectives. Because when people come up with new coatings, or they come up with new photovoltaics or new electronics, the whole point is we know it works on the ground, but we always have to do the space experiment to see what happens to it when it's up in orbit. And
Yeah,
so-
and as CubeSats get more and more longevity, because it used to be you'd launch them and they didn't last very long. And so you couldn't get long-term exposure information. But now as they're lasting longer and longer, we can get, we can put a small experiment on a CubeSat. And if it can go for a few years, you can get more data. But getting them down, it has to be something that's telemetry, because you can't hook them and bring them down. That was the beauty of the shuttle, is you could go up and put the suitcase back together and haul it back to Earth and evaluate it. With CubeSats right now, you launch them, maybe they'll fall down somewhere.
I think there was a.
We had an issue with NASA. We had an issue that things were shifting to life sciences rather than material science, and the biggest problem was simply power. Just didn't have the tools to do it.
I think we had a question down here.
Speaking of power, yes. You had the ultraviolet, converting those
downshifting.
sun's energy ultraviolet into visible light, so that way your photovoltaic cells could create energy from that. Are there any other bandwidths, such as you're screening for infrared now to try and protect? Are there any other wavelengths that you're attacking to try and squeeze more power out of the photovoltaic cells?
Well, there's a lot to do with photonic coatings, and so, I mean, even just for detecting different types of wavelengths to say, hey, if I wear something, it's like, I might get hit by UV. I can't see a UV with my eyes, so if I put some makeup on, and then all of a sudden I can say, oh, my face is glowing, then that might be, that has some utility over there. That's actually one of the things with the different types of microcoatings and whatnot, the white paint that was available. One of the big projects we worked on was little microspheres that if you design them, they're very, very scattering. And much to my surprise, when we started doing that, we found we could get those little microspheres very, very easily, just because they were incorporated into cosmetics already, just because people want to have a glowing face. And so, the question was, I think you're saying is, are we looking at sending it to different other wavelengths of light? It's like, yeah, that's actually very, very important, depending upon what you want to do. And so if we're thinking about multi-junction solar cells, the one big thing is that they're all lined up, they're all tied in series. And so in one case, I'm going to need to make sure that I'm going to be limited by one particular junction. And so if I can actually send my light to that one particular junction and focus and enhance that, then that becomes very, very, very helpful. Okay.
Hi. With the frequency of SpaceX launches and private space launch, how has the U.S. I guess my question is, how have we kept up with intellectual property? Like I know China is trying to replicate the super heavy vehicle, and there's a lot of, Elon Musk has mentioned that regulation is the big hindrance the U.S. space effort. So are we taking the necessary steps to stay at the forefront of this?
Well, it may be a little beyond my pay grade, but certainly Elon Musk's technology, he's gotten a lot of government funding. So he's kind of limited. There's agreements between he and the government. So are you talking about, are we staying up with the technology that he's developing, or?
I mean, I'm an American. I had a family in Ukraine, just like concerned citizen. I don't want to be left behind if we have the best and greatest technology to be operating right now.
Leadership, I guess.
The government is involved in SpaceX's and the Starlink all that, because there was government money involved in it making the Starlink constellation. There are going to be restrictions on its use or not use. But again, I'm not really, just from what I've heard at work. so this is hearsay. I'm not a lawyer and I haven't looked at the paperwork, but I do know that that the government will have something to say about.
But Aerospace Corporation is involved in.
We are involved in SpaceX in the sense that if we are helping with design evaluation, test and evaluation. There's been anomalies that propulsion anomalies. Our propulsion people have been called in to find out what's going on and fix what's going on. So we've been involved in what we normally do with commercial things. We're brought in as someone to help make sure that things get done properly.
Can I ask maybe an interesting follow-up that I was always wondering? I guess you can clearly see that right from sort of Tomči's talk, which is more academic-centric, right? Where you could definitely see that there's a lot of collaborations, right? International collaborations happening. I would have an impression that even in sort of more restricted areas like Donna and Tom, you guys work in. Still, the fact that there's more activity internationally on, let's say, purely materials development, right, makes your job in life easier in terms of discovery process, because if there's 100 people across the world working on similar problems, right, chances are somebody will come up with something. We're not siloed, right? You know that information, you adopt that in your work, and so the discovery phase process becomes more accelerated and more efficient. Is that true, or is that I have a wrong impression? That if there's more players in the world doing something, everybody wins.
So that's one of the things that I highlighted at the last slide that I have.
Yes.
The AFRL is very interested in trying to be able to broaden the knowledge of space and the technologies, and actually raise the level of scientific literacy within the United States and also throughout the world. And so that's why a lot of the stuff, if you talk about any type of DoD research, if it's basic research, we want that to be published. We want to have we want to fund scientists, we want to find academics, we want to have all the basic science being published out in journals. We want to provide educational opportunities. We love this Space Institute that you're putting on, because getting into space is very, very challenging because you have a giant hardware barrier. You need to have a lot of very, very sophisticated equipment that Donna pointed out over at the Aerospace Corporation, that we have over at AFRL. So if you have it at the university, now you have a lot of people who are coming in, they're getting that training, they're getting that education from all the experts that are here, and then as we start to build in more and they have these resources, then the expectation is that we'll be able to keep up, and we'll always be able to come up with new technologies to solve our problems. That's the big idea. So if you're saying, what are we doing to try to make sure we're staying ahead, or what's our plan to stay ahead, then the idea is educate our workforce, give them the tools that they need to be able to set out their ideas, get the tools they need to figure out when they're wrong. Because if you have a good idea and you're never able to test if it works or not, it's gonna stick there like an earworm. It's not gonna get out until you do that experiment. So you need to have that hardware available to people. So all that stuff is, which was highlighted, is over at the last slide. We put our money where our mouth is. We're trying to be able to give people those resources.
As Tom pointed out, basic research is publishable. If it gets to more and more applied, then you have to go through your legal teams to say whether everything has to be cleared for publication that comes out of our organizations. But if it's pure research, and you don't feel like you're feeding information to somebody that shouldn't get it, then it's fine. And of course we have our partners, the people we do partner with in Europe and Japan and all those places that we freely share information, right. Or we have agreements, or we have
And that's also just as the highlight, the last thing, the SBIR-STA program. We love to get people to get patents for what they come up with. Because the whole expectation is that the government doesn't want to be in the position of making money. It doesn't want to be in a position of trying to stifle innovation. So what we want to do with the SBIR program, STTR program in particular, is fund all of the people here, fund the general populace to come up with something, patent it, make a whole bunch of money on it, and then be able to sell it back to the government so we can use at a low and reasonable price.
Yes.
So,
Well, actually, some of these programs are responsible for our success as well because Oak Ridge operates in a very similar way. We're using it, so we are super happy to hear that.
and if you notice that as soon as Donna was saying, DoD is always releasing our basic science. So we're already saying, we're not going to patent that. You take that information, you go ahead and you run with it. Okay?
There's a bunch of questions back
Bunch of
there.
questions?
Question there.
Just a quick
Oh.
one. Fuel cells have a very niche legacy human spaceflight systems.
That is true.
Gemini, Apollo, Shuttle.
Mhm.
And it's not part of Orion, Starship, and Dragon. So what is the modern application that you're looking for?
Okay, so the whole modern application is a recognition. There's a couple of things. One is that we got a ton of people looking into batteries, right? So lots and lots of industry. So the expectation is commercial is already putting a lot of effort into it. If there's something to be discovered with a standard battery, lithium-ion type of technology, commercial sector going into it. So if we're saying like, okay, what's going to be beyond batteries? And then fuel cells is one thing that I'm looking into because fuel is just has much higher energy density. Outsurpasses everything else in terms of if you compare it to a battery technology. And they're saying, okay, well then fuel cells have been around for a long time. People have had this since Apollo, since on the space shuttle, they had it. That's because battery technology couldn't keep up at the time. So I would say batteries are doing very well right now. We haven't looked into fuel cells recently, and that's one reason why I'm looking into it now. And they're saying, what is the type of fuel cell that's looking at? I'm looking into solid oxide right now. And I would say that that's one thing that's not been investigated too much. Is that? Or somebody in the back?
Just a quick question. You know, we're always very impressed with the longevity of various NASA, the Martian rovers and the helicopters and so on and so forth. But it seems that so often they fail because of dust on the solar panels. You mentioned, I think, microspherules and anti-static coatings. How are we dealing with technologies or materials to prevent those solar panels from dusting over so that these missions can go to 50 times their anticipated energy
I couldn't hear that.
So it was a question about dust on solar panels? Or?
Yeah, could you put the mic up closer to your mouth? Oh, that's much
That's
better.
much clearer, yeah.
My question was, so much of the Martian equipment seems to fail because of dust on the solar panels.
Sure.
I mean, it seems like such a basic problem. And I think you mentioned microspherules and anti-static coating on panels, perhaps. How are we doing with materials or techniques, perhaps, to prevent that dusting of the solar panels so these missions will go much longer?
They're still there's been a lot of different ideas, like windshield wipers and electrostatic coatings, but then you have to power them so you can blast the dust particles off of them. And I forgot what else there is. There's nothing has really, it's not really well worked out yet from the last time I checked. It's still an issue. There's somebody in the back.
I think we had one in the back.
Poor
I mean,
girl.
dust is always a big thing, right?
Yeah.
So, and I mean, that's why we throw turkeys in jet engines to say if it survives. And so to some extent, that
The low
space,
tech.
yeah, low
The low
tech,
tech.
right. So the thing is, as more people get into the space game, as it becomes less and less you're using exquisite systems, then I would anticipate that we're going to get equipment that is just more robust. So we spit
Yes.
a whole bunch of dust in it, it's going to still function. So it's just a question of, was there a need? And in the past, there hasn't been a need because we haven't been rolling around on Mars. We've been rolling around on the moon. There's a lot of dust there. And so but there really hasn't been until very recently a big push for it. So,
Yes.
so I would say if you're worried about dust, I would say it's more during the assembly time that people care
but we
about.
were, when I did proposal evaluations, that was an issue because it
Sure.
was for the Mars,
Yep.
So that was like, how are you going to address this?
Mhm.
And I still don't think there's like the best, I don't think, wow, we've solved that problem. I
Sure.
don't think that's happened yet.
Okay.
Could you bring your mic closer to? That, it's
Is it
better.
on?
Before
Elon Musk came on the scene, all the basic science, all the actual application, things going into space were done by Gabrielino, Caltech, myself. So my question is, if Elon Musk is also sponsored, funded by the U.S. government, how do we deal with all the commercial aspects and the profits? Because when I try to buy SpaceX stock, you have to buy Amazon. Alright? And I know that he's also using Tesla. All of this are connected. So my question is, yes, we have such a powerful global player in geopolitics. So I'm really wondering how does the whole international community deal with that? And we talk about satellites from Ukraine or phone access in disaster areas. The other question I have is, he's putting up so many satellites out there. So wouldn't he also have a responsibility, having technology to clean up, there seems to be no commission, international commission to look at the amount of pollution or the debris engine. So I'm just curious, who is dealing with all this? Who has most responsibility?
Okay. I had trouble hearing.
So I think the question was, are we worried about just one person defining space? Is that one of your first question? One of the things. And so what I would say is, at least in the talks that we presented here, is that we want to have many, many players. We don't want to have a single person be able to de facto leverage so much power to be able to say, we're going to do this, we're going to do this, we're going to do this. We want to have an open competition. And that's why with every type of government opportunity, it is always an open competition. Everybody can apply for this or that type of grant. There's no specific, or at least I'm not aware of any particular program where people say, oh no, you're definitely going to pick this person, you're going to definitely pick that person. So if you have a brilliant idea, government is always, as we had mentioned, is providing all that basic information, all that basic knowledge. If you can take all that basic knowledge and you come up with a new space technology, then we're happy to support you using all the different types of programs that was mentioned before on the different slides. Okay, and then I think you had another question? If he has to take that goes into, as a commercial enterprise, he can just, if he got the regulation, he got approval, he can just do it. So unless people put in a law to say you got to clean that up, then there's not much you can do. Sure. Well, that goes into all the big discussion about government and entrepreneurship and whatnot, because an entrepreneur is going to look out for their interests, rightfully so. So if there's concerns, and then there is concerns about like, hey, we got to be doing this, we got to be doing that. That's why NASA's looking into cleaning up all the debris. So yes, there's definitely concern, but if you're saying, is the private sector going to be doing into it? They're not going to unless we set up the situation that there's incentivized to do that. And so what's going to be the incentive to do that? There's a lot of factors could be there. You could say like, okay, it's a regulation. That would be an incentive.
Right.
I would say that the private sector in its interests would be, if I'm a space company and I'm going to make space ruined forever, that's going to put me out of business. So I would say that they also have a commercial interest to make sure that space is always available for them to capitalize on.
And certainly
Okay,
satellites for the military or for the government are going to have their regulations. Because when I started in this field, there was no plan, there was no requirement for a plan of what are you going to do with your dead satellite once its mission is over. Just let it float around. And the government said, this is becoming a bigger and bigger problem. We have to come up with a way to decommission it. Either you send it back to Earth, you have to blow up or drop it, you have a little amount of propellant to shove it down, or some propellant to shove it way up and out of the way. so into deep space. So that did not exist when I started in the space industry. That became a requirement. Now all government satellites have to have, you know, you know, what do you do at the end of life? You have to do something with your satellite. You just can't let it float there forever. You got to send it way up or way down, and that's it.
Okay, I think we're actually running quite a bit over time, so please remember that we have a reception and our panelists will be available. But I just wanted to wrap this up by giving each of our panelists just a minute to close off and just say, what are you most excited about? Where are the big discoveries in your particular area coming from? Where would you be focusing your areas now if you're a young researcher just coming into the field? And so maybe, I know it's a zinger, but you know, a kind of a knee-jerk response would be great. And so if you want to take you know, just 1 minute each to let us know.
Me?
Up to you.
Up to me?
Go for it.
Rock, paper, scissors. I would say that whatever you're working on right now, whatever's capitalizing, what captures your imagination, any type of interesting phenomena, you're all incredibly intelligent and creative. If it captured your interest, looking at the broad diversity of technologies that the AFRL is looking at, I am pretty confident that we're going to be able to leverage that to do into a unique space capability. So look at what you have, what's exciting you, talk to other people about it, let's make a widget out of it.
I would say yes, yes, yes. And if you don't know what's out there, get different bits of information, brochures, what kinds of, like I said, the aerospace, I gave you a little smattering. We have publications that say, what are the labs doing? What kinds of stuff is on the cutting edge right now? And if that can inspire you into coming up with creative ideas, that's what we hire people to do, is to come in with great ideas and change the landscape. So it may be something I'm not working on carburetions anymore. So I've done a lot of other things that are really exciting though, and every time I learn about something new, I get excited about that. And so you're gonna be constantly evolving. You might wanna get some of these publications from the government and from the national labs and from universities and FFRDCs, and just look and see what kinds of work are people doing, and does that sound exciting? And then you can make inquiries and say, what can I do to get involved in this?
So what I would say is we've been very human-centric, and I understand why. The government and the industry needs to focus on getting us out of space, giving us communication, so on. But is there any need to be so human-centric? Dragonfly will reach to Titan. The Clipper will reach to Europa. Both places, there is a very, very high chance of detecting life. And I think that should also be for us to think in the future, instead of just looking at us and how we look at space, but just to face it. We might not be alone, and that it's striking our ego, but we should look at with a different perspective. I think that more funding should be directed into that kind of crazy ideas, not just something that can give us immediate benefit, but something that we can look at as humanity. Because just to remind you that we started just looking at the sky and dreaming, and right now we are just looking at the sky and we are thinking which one will be the first company to reach and put a hotel there. I think we should go back a little bit more and be dreamers.
Okay, so with that, on that very positive, futuristic note, I wanted to, first of all, thank our panelists again for fantastic and fruitful discussion today. So, Jacob and I really thought, hope that this was a thought-provoking and impactful event, and your presence here was, thank you for all those who asked the questions and staying engaged. I wanted to say a couple of things before we move to the room next door. Very importantly, I want to thank Andrea Corrales for all her work organizing this event. I also would like to thank Lloyd De Leon from our development team, again, spearheading the effort in organizing this. Also, huge thanks to Penny, who's been our dedicated videographer for this and many other events. And so with that, you know, we would be delighted to have you at the reception next door, which was mentioned, I think, already 15 times. So right here, you can't get lost. You walk out to the left. And so we hope you enjoyed this very unique conversation. We thank Space Institute and the Division of Physical Chemistry for really allowing Jacob and I to, you know, be creative and have something like this, and hope to see you next time. Thank you.